In this video, we're going to talk about logarithmic functions. So this is our first introduction to something that we have never really had experience with before, unless you've taken this class before. Before we jump into what a logarithm is, let's review really quick how to find the inverse of something. In particular, let's find the inverse of this exponential. So here, let's just write the steps one more time. So first step, you rewrite f of x as y. Second step, you switch the x and the y. Third step, solve for y. And then last step, you rewrite y as f inverse of x. Okay, so let's do that for this function right there. So we'll start by first rewriting it with a y. F of x is y. Now we will switch the x and the y. And to solve for y, we actually have a problem. We can't solve this for y. So that's where logarithms come from. Because this is technically the inverse, like this is the inverse of the original function, but we're unable to solve for y. It looks exactly like the equation above it, right? I mean, the x and the y are switched, but it's a base 2. We have an exponential function. So it's problematic. So this is the inverse. Mathematically, we have found the inverse, but it looks similar, too similar to the original. And for that reason, that's what the logarithm was created to be. It was created to represent the inverse of an exponential, but look distinct, so that it no longer looks the same as the original function. So the logarithm is the inverse of the exponential function. So a logarithm base b, written log base b of x, is the inverse of the exponential function base b, b to the x. And here is the big key for logarithms. The statement b to the a equals c is equivalent to the statement log base b of c equals a. So that is a base b, and that is an L. So it's like a subscript. It is a subscript. So here, let me make sure it looks like a subscript. So these two statements are equivalent to each other. To say log base c equals a is the same thing as saying b to the a equals c. So before we write the properties of logarithms, which are the inverse properties, I want to practice rewriting an exponential statement as a logarithm and vice versa. So we're going to jump to the next example. We'll come back to the properties in just a second. So let's rewrite these as logarithms. So as a logarithm, this is log base 2 of 8 equals 3. Log base 2 of 8 equals 3. So the number that we're raising to the power, the base of the exponent, becomes the base of the log. So this one is going to be log base 5. And then instead of, we take the opposite, where it's opposite of the equal sign. So log base 5 of 25 equals 2. And then here, log base 10 of, I'll put it in parentheses, 1 over 1,000 equals -4. So these are the equivalent logarithmic statements of those exponentials. So all three of these logs mean the exponential statement. So let's look at a logarithmic example and switch it to exponential form. So this log in exponential form would be 6 to the 1/2 equals the square root of 6. That's the exponential version of that logarithm. And actually, it makes sense, right? That literal statement is a true statement. Okay, so for the next one, 3 to the 2 equals 9. And switching out of logarithmic form is actually a little bit easier than putting something into logarithmic form. There's like a pattern I follow. I take the base on the logarithm, so it's base 3. I raise it to the 2 and then set it equal to 9. So I follow that pattern. Base 6 raised to the 1/2 equals square root of 6. So it's kind of like a little circular pattern I use when I'm converting a logarithm into exponential form. Now we're more comfortable with exponential form because we know what that means, but the logarithm really is secretly exponential form. Okay, now I want to go back up and let's write the inverse properties that are going to occur simply because the logarithm is the inverse of an exponential. So if you take the log base b of b to the x, so these are the two things that are inverses of each other, it's going to equal x. And if you take b and raise it to log base b of x, it's going to equal x. And really what it's saying is when the bases are matching, they cancel out. Now, it's not really canceling out. They're undoing each other. They're, the inverse property is doing like a reverse operation. It's the idea that when you have an x and you add it to a negative x, they cancel out, right? They become 0. That's because they're inverses of each other. They're additive inverses of each other. So we can think of it as canceling. It is. And it's okay to think of that as canceling in your brain. But that's really what's in essence happening. Actually, for proper English, I should probably put cancel, not canceling. All right, so we'll come back to some of those properties soon, the idea that we can do some simplifying with logarithms. But honestly, the key for logarithms is this up here, what I've highlighted, to know that b to the a equals c is the same thing as log base b of c equals a. All right, that's the most important statement to memorize in regards to logarithms. Okay, so let's look at some examples. For instance, let's try to solve for x. We really only have one trick with logarithms. It's to change it to exponential form. So that's what I'm going to do. I'm going to do my little trick of taking the base of 4. I'm going to raise it to 2 and set it equal to x. So 4 raised to 2 equals x. And actually, 4 squared is 16. And we've solved for x. So that ended up being very simple. Okay, now, we will get to more complicated equations later. Before we do that, there's some other important things of logarithms that we want to cover. In particular, there are 2 logarithms that are so popular that they're given special names and they are on your calculator. And the first one is called the common log. And that's when we're looking at log base 10. In other words, if you have, I forgot the O, log base 10 of something. So that's so special. It happens so frequently that they stopped writing base 10. They just wrote log of x. And everybody knows in mathematics, that's base 10. So if you see log of 5, that means log base 10 of 5. That's what that represents. But the base is so common, happens so frequently, they just stopped writing it. They got really lazy and stopped writing it. And it's referred to as the common logarithm. The natural logarithm is log base e. And it has a special notation as well. Wow, that doesn't look like a subscript. So log base e is referred to as ln of x. And both of these can be found on your calculator. Usually they're like right next to each other. So our calculators can do log base 10 and the natural log. So the common log and the natural log are both on the calculator. They're just that frequently used. Now, the common log base 10 makes sense because our number system is base 10. So it makes sense that that one's so popular. But as I mentioned when we talked about E is a number that occurs in nature. It's something that was discovered from studying growth in populations in nature. And that's why it's called the natural logarithm. And it's used frequently, especially in science, which deals directly with what happens in nature. So those two logarithms are special and have special names and special notations. Okay, so let's go ahead and look at some examples here. Let's evaluate log of 1,000. Now, this is the common log, which means it's technically log base 10. Now, we only have a few tricks for logarithms, okay? We only have a few ways to deal with it. There's a couple ways we can approach this. I like to approach it using the fact that I can change this into an exponential if and only if I set it equal to something, which I'm going to call x, because I know we're trying to figure out what this equals. And if I wanted to solve it, I could just set it equal to x. And now I can change it to exponential form. So 10 to the x equals 1,000. So I've got to figure out, what do I have to raise 10 to equal 1,000? And the answer is 3. Now, that's one way of evaluating this. Another way of evaluating this is to use the properties of inverses we talked about earlier. So I could rewrite 1,000 so it has the same base as 10. I can write it as 10 cubed. And now using the property up here, I'm going to scroll back up here, the property up here where if the base matches, these two bases match, it ends up just equaling the exponent. That's what that's going to become. So scrolling back down. So this is going to be 3, which is the same answer I got over here. So these are two ways you could approach the problem. Both of them work. Neither of them is superior. All right. But we weren't allowed to use the calculator only because it said to use the definition. I would, however, take a second, grab your calculator and plug in log of 1,000. And if you do that, you're going to get 3. So just to kind of verify that that's what happens. Now, I realized too late that there's actually a typo on the next problem. This is not supposed to be an x. It's supposed to be an e, the natural log of the square root of e. So let's find the natural log of the square root of e. So natural log is really log base e. And the square root of e can be rewritten as an exponent of 1/2, which means this equals 1/2 based on the inverse properties of logarithms. Or alternatively, you could set it equal to x and change it to exponential form. Okay, let's go ahead, grab your calculators again. Let's find the log of 500. This time we're going to get a decimal. And plugging that in, if you need to pause the video before I say it, go for it. But I get 2.698, and then I'll go ahead and say 97. So we could round that, I suppose, but that's a good stopping place for it. And I guess depending on the problem, round it based on what it says to round it to. But there's the basic introduction to logarithms.